is Orit from the core Ceph team. Talk a little bit about our object storage, the Rados Gateway in Ceph. So,
hello. Thank you for coming so early on Sunday. I know it's hard. I'm Orit. I'm part of the Ceph team in Red Hat, and I work on cloud object storage in Ceph. And today we're going to explain what cloud object storage is, how it's different from regular storage types, a little bit about Ceph. So first, who uses Ceph? Not much. We need more hands. So we explain what Ceph is, how it's built, and then we talk about Rados Gateway, who is the part of Ceph that provides cloud object storage interface. And hopefully we'll have time for a few questions. So in general, I prefer people to ask questions during the presentation. So if someone needs a question, just raise your hand. So let's start. What is this cloud object storage? So we have block storage. Anybody uses block storage? Yeah, of course. We all do. So storage is divided into those fixed blocks depending on the device. We don't have any metadata related to the data. You just write the data somewhere in device offset left. And the application needs to manage to know what exactly is written there, where it's written. You can have several devices. But it's really fast, well, for storage. And today with HSD, it's really fast. You have the regular protocol, fiber channel, SCSI, SATA, iSCSI, and some people even use fiber channel over Ethernet. But using block storage is really hard for applications, so then came file systems. So here the data is organized. We have hierarchy of directories that can contain files and other directories. We have users. We have metadata for this data. The file can be in any place. You can overwrite it in the middle and allocate on demand. It's much easier for the application to use the storage, but it's slower than block. There's lots of arguments sometimes with file system people, but it's slower because of the whole metadata and hierarchy handling. Not all file systems, but many have sharing semantics, so you actually can lock the file for read-only or completely for you, and two different applications can use and write to the same file in the same time. We have local file system protocol like XC4, XFS, and so on. And we also have network file protocol like NFS and SMB. And FP is the Apple protocol, but that last they decided not to use it anymore, and they're moving to SMB. But then came something new. It was the cloud. So we had the problem before the cloud came. We saw the storage is growing and growing. So people moved to more distributed storage systems. And writing a distributed file system is really hard. I don't know if many people have tried. Writing a regular file system is hard, but when you try to distribute it, the metadata, you need to sync it all around is a problem, and the hierarchy is a problem. The cluster people here can say, agree. But in the cloud, it became even harder because we're not only talking about a large amount of data that is accessed all around, but we're talking also a large, really big data chunks. And then came one company, and then came the object storage that existed before the cloud object storage, but it was mostly like a niche, I guess, and I did research stuff on object storage, but it wasn't used as a standard. But nobody used it. But then came Amazon, actually, And when they started their own object storage, it caught up. I remember it was something like, I guess, 10 years ago when S3 was launched, and I thought, wow, this is the way to do storage. How can it? I thought it really is amazing as a storage person. I was then in IBM research and actually said, no, we need to do something like that in IBM. But of course, IBM is not good at being innovative, and they never did anything like that. So the idea is very simple. One, we're talking about cloud environment. So you want the API to be really for cloud. So that means it should be HTTP based, so that's REST API. And you want some organization of the data that the complex hierarchy file systems have is really hard. So it's just two levels. You have these, Amazon called them buckets, Swift called them containers, we have pools. So just a container of objects is the way to organize your object into groups and maybe add some properties for that. So that's bucket, and inside the bucket you have those objects. And objects are not just data. You have a name, you can add them all sorts of metadata. Some are fixed and some you can decide on your own. So you can later find them and know what's the data in them. You have users and tenants, which is like an umbrella for users to share the same data between them. You have authentication, ownership, access control list. And we talk about large objects, really large. So that means you need lots of storage. Because there's a large object, usually objects are immutable. That means you write them once. If you decide to change them, you need to actually overwrite all the objects. You cannot write in between. And it's much more efficient for those large objects to be immutable, and it simplifies the allocation. So the protocols today, the most common one is Amazon S3. It's the richest one, and I don't know what scale Amazon is, but I'm sure it's huge. I cannot imagine how much storage S3 has. In OpenStack we have Swift, and there's also Google Cloud Storage. So this is the example how the API looks. Put, writes an object, get, this is a bucket. So put create an object, bucket, get, read the bucket. You have actually, can be more complex because you can read also the metadata using head. You can delete a bucket, create an object. But it's not as simple as that. You have copy operation. This is actually a simplification because as you see there's some headers there. Usually there's lots of header that says all sorts of metadata or maybe make the operation more complex. So we talked about really large objects. Anyone here ever downloaded stuff from the internet and you lost connection and you need to restart the download? Everybody. It's really annoying. And when we talked about large objects, we can get to giga size. So this can be really hard. So for that, we have the Multipart. You want to upload or download an object, but you want to maybe stop it, maybe retry. So you take a big object, you divide it to small parts, and each part is being uploaded or downloaded in parallel, so you can handle network problems, and then only you can continue where you stopped. And you can stop, start, uploads, download. And also it's good for streaming, for example, when you don't know the size of the objects you're actually going to upload or download. Download usually knows, but upload, you sometimes generate the data when you upload it, and for that you use Multipart. But it's harder for the storage because until you finish your upload, you don't know what the object will be, and we cannot commit it, so we need to start all those temporary parts. And sometimes you will have failure and we start the upload completely again, so we need to, in the background, to clean all the extra stuff we got. Another feature, which I really like, so here, whoever used here VMS? Oh, no one, yeah. So, remember VMS? We had file versioning. When you write on a file, you get a dot something. I really liked it because I sometimes do, by mistake, delete stuff. It's really good. You always have the previous copy. So again, in cloud storage, we have versioning. By default, buckets, it's per bucket. By default, buckets are not with versioning, but you can enable it, and that means when you override the object, it creates a new object with a different version. If you delete the latest, you will still have the old version. It's really helpful when you delete stuff by mistake or overwrite by mistake an object. And cloud objects has other really, really cool stuff. I didn't talk here about authentication because every protocol does it completely different. The main difference between Google Cloud Storage and S3 is authentication, and it's incompatible. Swift does it differently. So some use user passwords, some use user and a key and a secret. Everything is really different. So authentication is complex, and we have object lifecycle. For example, you can set a date in an object, and when it gets to that date, it's called object expiration, the object can be deleted automatically or moved to cold storage. And lots of cool features. Any question about cloud storage? Okay. So let's talk about Ceph. So Ceph is, shortcut was Cephalopod, which is the family of octopuses and squid. So all our versions are called of one animal, that name. So the latest stable version is Joule. I think that one is Joule, if I remember. So Ceph is open source. This is our GitHub. We have Ceph.org. Under it is all the Ceph code. It's not only Ceph. We have our own testing framework called Tautology. It's also open. And we have additional tests, like we have S3 tests that test S3 compatibility. We have other components of Ceph. So Ceph is open source. We are in FOSDEM, so it's open source, LGPL. It's software-defined storage. Well, we are in the software-defined storage room. That means it can run on many kind of platforms. You can configure and adapt it to different topologies and scale. It's distributed system, and like a distributed system, it doesn't have any single point of failure. When you have a large number of nodes, you cannot handle a single point of failure because you assume everything will fail. Large scale means failure happens. It's massively scalable. It was built to be large scale. So we say POC can be 3 nodes, but the minimum is 5. And I actually recommend more. It's a large scale system, not for 2 nodes, 3 nodes. Because we are large scale, we assume that we have to either replicate data or use erasure coding to be more efficient space, because we assume the data gets lost, so we need more copies. It's a large system, failures happen, so we want self-healing because you cannot handle those failures manually. Everything should happen automatically. And we have unified access, so we have CephFS is the name. It's the file system access. It's a POSIX-compliant file system. You can use our client, Fuse, or our kernel client, and there's integration to OpenStack Manila. And you can use NFS Ganesa with it for NFS and Samba for SMB. RDD is the block interface. Many know it from OpenStack. It's integrated completely with QEMU. So you can use it with QEMU for Zen or QEMU for KVM. And you can use a kernel client if you want your own block device. And we have Rados Gateway, which is a component that provides the cloud object storage. Underneath this all, we have Rados. And I'm going to speak a bit about Rados. So Rados is a reliable, autonomous, distributed object storage. So as you see, it's an object storage, which is interesting. So when Ceph started, it was to build a very fast, scalable, distributed file system. And they started with Rados to be as the rich object storage that you can build the file system on it easier, at least. But writing distributed file system is never simple, even if you have distributed object storage underneath. And in the meantime, we took to develop CephFS. We started RDD and Rados Gateway. And now we also have CephFS as production. So what Rados does, it does all the distributed stuff. So it does all the replication or eraser coding. It's a flat object namespace, and we have a pool of objects, and we can configure each pool. It could be a pool of fast storage, SSDs, or a pool of slower storage with a hard disk. It could be different application. It could be freeways, or it could be eraser codes. Ceph is a strongly consistent system, and it's software defined. That means it's aware to the infrastructure and the topology, and you can match it to different architectures and systems. For placement, we have a hash-based algorithm with no lookup called crash. And we want performance, so we serve the data directly to the client. So a little bit about crash. Crash is our placement algorithm. And we wanted an algorithm because it's a large-scale system that doesn't require any lookup. Lookup requires some central area. You keep the table of the lookup. You can replicate it, but it's not very efficient in large scale. It's a bottleneck. So crash doesn't require any lookup. It is topology aware. So that means you can actually put in you can say this is a rack, and I don't want to place two copies on the same rack. So you choose nodes that are not on the same rack. You can configure the application. You can do weights. And it's really fast calculation, deterministic, and it's evenly distributed. That's why we call it pseudo-random, because that way we can benefit from all nodes. So a Ceph Rados cluster has two kinds of node. The first one, OSD, object storage device. Those, we have lots of those nodes, daemons, tens to 10,000. I think 10,000 is a lot, maybe thousands. And we have one OSD per disk. You can put an OSD on a RAID, but it's a bit a waste because we do the replication ourselves. There's no reason to do additional replication in the storage layer. And its main thing it does is serve the object to the user. It's a smart storage node. That means it does peering, and in case of a failure, it does the recovery automatically. The OSDs are talking with each other and will replicate the needed data, or if a new node comes, it will rebalance the storage. The other kind of nodes we have is the monitor nodes. They store all the clustering logic. They maintain the cluster membership, so if an OSD fails, the monitors get a notification because it still will notice that the OSD is not responding, and it will notify the monitor there's a failure, and then the monitor will spread it to the other OSDs. And when you add an OSD, it's the same way. We have a small odd number of those nodes, 3, 5, so on. They do use Paxos. It doesn't store any data to the users. It's just for the cluster memberships data. So we have this cool object storage cluster. We want to accelerate. So there's Librados, and you actually can use Librados if you want. You have your own application, and it really needs lots of performance, and you're willing to actually interact with the Rados API directly, and you can use, we have actually some users use Librados directly. It has binding to C++, C, Go, Ruby, Python, I don't remember, probably more. And it's a very rich API. It's not just read, write, object. You have a key value store, we call it OMAP. So inside one object, you have a key value store, and you can use this to store, for example, the file system stores the directories in an OMAP, and Rados Gateway, the bucket index is the OMAP. It supports atomic single object operation, so you can update the attributes and keys and data on an object in one operation. It has snapshots per object. Objects are mutable. That means you can actually partially overwrite objects. And we have Rados clusters are very similar to storage procedures on a database. You can actually write code that will run directly on the OSD when an object is changed. It's really a strong feature. It allows lots of performance. We use it all around the services. And we have a watch notify service, so you can register an object, and when the object changes, we get a notification across the cluster. Everyone registers that notification. So it's a very strong API, but it's not a standard API. It's not block, interface, file, or object, a cloud object. It's your own, and if you really import the performance and you're willing to make the effort, Librados will be really cool. Any question about Ceph in general? Yeah.
Just a few words about Ceph. What's the approach you use?
Okay. So first, all these are divided into placement groups. So all OSD need to replicate one another. One can be the master in some case. In other cases, just be a replica. So they talk with each other, and they can detect when there's failure, because they need to talk with each other, and then if they get an error, they notify the monitors, and then the cluster starts to handle that case. So you need that OSD that failed. It's takes a while to mark it as failed, but when it's failed, you know all the data it contains need to be replicated to other OSDs, so then they do it automatically.
One question about the object storage. Each node has a complete set of the whole object?
Well, depending on the size of the object, but our maximum size of object in the Rados is 4 mega, so 4 mega will be let's say you are FreeRes replicate, so FreeResD will have those 4 mega. If the object is larger, then it's more.
I'm sorry, my question is the object distributed, that it means you have to have a set the storage nodes to have to retrieve the complete object?
No,
Go
no.
to the site?
No.
You need just one.
Yeah, you need one to read. Yeah. To write, you need 3, let's say. Or if it's 3 ways, you need 3 copies. We write 3 times, but you read, you would need 1 copy. Yes?
Is it better for Ceph to have many lower quality machines, or is it better to have a fewer number but higher quality machines?
Many lower. If that's the divide, of course we prefer many high quality. Yeah, but the more you have machines, the more you can do large scale. Now we're going to talk about more about Rados Gateway, which is the component in Ceph that provides the cloud object storage. So like all the components of Ceph, Rados Gateway uses Librados to communicate with the Rados cluster. So we have this cluster of OSDs and monitors, and that's where the data is stored. And Rados Gateway is a service built on top of that. So Rados is object storage. So that's cool, it should be simple. We can have cloud object storage. But life is never simple. So it's not just to provide the REST API and matching the API we have. When we look at our object for Rados and Rados Gateway, or cloud, we see some difference. So first, Rados, the biggest size of an object is 4 mega, and we're talking about cloud, so we're talking about really large objects. So we'll need some way of taking big objects and divide them to those 4 mega size objects. So Rados objects are mutable, but in cloud we talk about immutable objects. The hardest part is that the pools inside of Rados are not indexed, but user want to list all the objects in the bucket sorted by name. That means we'll need to add some indexing for the bucket to allow those listing. And Rados says per pool SEL, so pool is like a bucket, but we need SELs per object. So even in spite of the fact that Rados is object, we still need to add a layer to implement the cloud of the storage on top of it. So we have the Rados cluster. We save all the data inside the Rados cluster. Rados Gateway is stateless, so in case you see that you have lots of actions and operation, and the Rados Gateway is loaded, you can just run another instance of Rados Gateway on the same Ceph cluster, and both can work together and continue. And that way you can scale up. So again, this is object storage. We have users and tenants. We have buckets, object. We have metadata per bucket per object. We have access control lists per bucket per object. We have authentication, which is really complex because we support several protocols. Today we support 2 cloud objects protocol, S3 and Swift. In many cases you can use both in the same time, but sadly they are not compatible, so there are cases that it won't work. You cannot upload Multipart with Swift and read it with S3 because they sign differently, they calculate the signature differently. Versioning is very different. You cannot use both. Version bucket from S3 will not be version when you access it from Swift and the other way. Authentication, of course, is very different, but we do support Keystone for S3, so that's maybe okay. We also support NFS. When we say, but NFS is a file protocol. Yes, it is. It's not a full NFS. If your main workload is a file system, the Cephfs, It's for users that mostly use object storage, and they can use the NFS. We use NFS Gemisha on top of, we call it a library, we call it lib RGW, to allow that. And it's for migrating from NFS to object storage, or exporting a bit. And also, if you have this legacy application that needs this NFS, very basic stuff, then you can use it. But for full-scale NFS, you will use CephFS or other NFS stuff. So we try to build Rados Gateway as layered as possible. So a request goes through all the layers, one after the other. We have two layers, three parts that everyone can access all the time. I'll go a bit about those. So first we have the front end. Front end is what provides the REST API actually. So we need HTTP. So we have two ways. The first is the old and unrecommended way. So we support FastGGI with Apache and probably other web servers. The reason it's not recommended is because FastGGI has lots of security issues. So, but sometimes if you already have your own Apache and you handle the security issue with FastGGI, it can be an option. Today we have also from Hammer, Firefly actually, maybe, I don't remember. We have Civet Web. It's an embedded web server inside of the Rados Gateway. So we recommend that. Then we get to the REST layer. It's actually the layer that converts from past the dialect between the protocols, so it passes S3, Swift, and other API. Then it goes to execution layer, which is the common layer for all protocols. We don't want to write code twice, so we try to use as much as common code handling different protocols. The next layer is the layer that talks to Rados. It's not enough to use Librados. We need to do some stuff on our own. So for example, I need to get faster. We do the object striping, atomic overrides, and all the bucket index handling. And we also, it contains the object classes that run on RST. We have quota, and we have quota per user, quota per bucket. We have the authentication layer because in many cases, in many layers, you will need to sometimes you need to authenticate again. So we support the AWS 3, AWS 4, Keystone 2, Keystone V3, LDAP. There's work going on STS, but hopefully it will be in end of Kraken or maybe in Luminous. Objects are large, so we don't delete them and free the space immediately because it takes time. So they move to a garbage collection, and in the background there's a process that cleans the large objects. So I don't have time, so I'm going to skip some slides. So this is how we build object. We take an object, we have a head object and tail. All objects have a head object. It contains all the object metadata and attributes, and up to 512 Ks of data. So small objects only have an head. Large objects are striped, and they have several tail objects. To have a fast access to objects are names inside of Rados, looks something like that. So the head, the number 123 is the bucket ID. It's not the name because bucket, you can rename buckets, so it's a unique ID for bucket. And then the object name, that means that we don't need to do any lookup in order to read the head because it contains the metadata, and we want, many cases want to read the metadata fast. And then the tail is the bucket ID and then some UUID, and the part. A little bit of bucket index. So bucket index is just all the objects in the bucket sorted by name. But when we talk about cloud-out storage, we have cases that one bucket contains millions of objects. And then the bucket index is also a bottleneck for performance, and also because it's in the end stored in an OBAP, Rados object. If we pass one object line, it's also inefficient. So first thing, if you have lots of objects, the Ceph number is up to 100K object per one bucket index, that's fine. If you have more than 100Ks, then you need to use sharding. We collect the bucket index and split it to several objects. Depending on the number of objects, you decide what number of shards you want. We have now support for offline resharding. So in case you didn't reshard the bucket and suddenly you got to large number of objects, you can reshard it. I think it's even in Hammer, the latest Hammer, the 10, and will be in Joule and there's newer versions. And we're trying to work on the online resharding that you don't need to offline the bucket and stop I/O to it. You can do it with I/O. We skip that. So our quota is we are a distributed system. Objects can be written from many places, several Rados gateways. We need some way to coordinate the quota. So we use the Rados class objects to do that. So when we actually write the object in the OSD, we update the quota. That means the quota is not completely consistent. We sometimes mix a bit, but I think file systems have the same issue with that. We have a metadata cache, and we use watch notify 200 dots. That means in case the metadata change, the other Rados gateway gets a notification and then can invalidate that entry from the cache. So multisite. So we're talking about cloud, but cloud is never one data center. Many times we want several data centers, and we want to have either disaster recovery or actually want to use all of them. For that, we have Multisite, our RGW application. So you can take two Ceph clusters, and you need to configure them, and there will be an asynchronous application around each other. It could be active-active or passive-active. The metadata operation, which is user creation, user deletion, bucket creation, bucket deletion, and a few bucket metadata operations, are synchronous because they are really important stuff, and we cannot have a difference in those. So we have a meta master, and in case he fails, you need to do failover and configure a new meta master. But the data is completely asynchronous. That means all different Ceph class, in different clusters, you can update the object, and they will be replicated automatically to the other clusters. A zone is like what we call a Ceph cluster. So if you have two locations, each one will have a Ceph cluster that will be two zones. A zone group is just a group of zones that share the same data. So even then, not in the same location, they will be in the same zone group because they replicate from each other. We have all multi-site support in Hammer. It's called the sync agent. It's only active-passive. But from Joule, everything is active-active. I don't have time. Okay, more stuff. So we have, we talk about object lifecycle. We don't support the full S3 object lifecycle. We have object operation and basic storage policy, which means where after the object expired, to move it to different colder storage. We support we have more efficient object copy operation. We don't actually copy the data, but just update the object head to point. So we know it points to the same data as a different object. We have encryption thanks to Mirantis. So all objects are encrypted. We have compression. Also Mirantis work. We support torrents. We have static website to anyone who wants to use static website. We have support, that's new in Kaplan, it's not detective view. We have metadata search. You can do exported data to Elasticsearch, and that way the user can search the metadata. And we're working about doing online bucket resharding. I hope I have time to questions. No. Okay, questions? One. Yes.
Is there, or maybe what is the performance setup for the Rados Gateway rather than where you compare it?
Well, he asked what's the performance penalty of using Rados Gateway and not Rados directly. So you need to understand they are very different. Rados is REST API. So REST API is HTTP. That's slow. It's a slow protocol, HTTP. So I think that's the main performance penalty. But if you're talking about really, really large objects, then I think the HTTP is limited. We have some overhead. We are not as Rados bench because we have per object also X attribute updates, not just an object. So I don't know the numbers, but there's apparently. Thank you.